Well, thanks so much for having me. My name is Ramon Weber, and I'm an assistant professor at the Department of Architecture and joined Berkeley last fall. Maybe some of you saw my presentation in the fall CBE meeting, and so I'm basically the latest addition to the CBE research community. And my research is bridging the gap between computational design and building science. And today I want to share some of my work on building stock analysis, both for embodied carbon and the reuse potential of buildings. And so the challenge around finding better ways of building becomes clear when thinking about the magnitude of construction that is going on. And the UN predicts that we will build the equivalent of a New York City every month for the next 40 years. And so that means that we need scalable strategies to reduce embodied carbon, and especially when it comes to building materials. And the scalability of these strategies will have a profound impact on how we will kind of lower the emissions. And in the built environment, we have this dual challenge, right? Where on the one hand, we have carbon emissions. And when we look at global carbon emissions, I think everyone here is aware, right? Buildings, they use almost 40% of the world's carbon emissions, kind of contributing through direct and indirect emissions. But also when we look at waste, here I showed a graph from the EU, like looking at kind of how waste is distributed across the economy. And you can see that also there, the construction industry contributes 40% of the waste of the whole kind of industry. And so the use of materials is, of course, directly related to the embodied carbon emissions. And when we talk about reducing waste and carbon, it's, of course, obvious that scrapping building materials before they reach their end of life is a bad idea, right? And so thinking about buildings at the end of their life, let's take a steel building, for example. Well, steel is usually scrapped upon demolition. Now, it travels to a steel recycler, and steel recycling sounds great, right? But in the case of steel, recycling means remelting the beams in a furnace. And while the majority of the steel recycling is done in an electric arc furnace, some furnaces still rely heavily on fossil fuels. But also the electric arc furnace uses a lot of electricity, right? That usually doesn't come from renewable sources. And so this has profound impacts, and the steel industry accounts for over 25% of industrial emissions and around 10% of energy-related CO2 emissions. And so going back to buildings, I want to kind of tackle these two main research questions. How can we predict material quantities in existing buildings? And could we maybe use this information to increase future reusability of the building components that we already have and have produced? And then secondly, could we lower the embodied carbon of new buildings that we create in the first place, right? And so to start answering these questions, I want to give you a quick overview of some of the different ways of how we currently estimate embodied carbon in a building. And the first one would be through real or synthetic high-level data, right? Usually this data comes from surveys where architects or engineers report on the embodied carbon of their buildings. And typically this data is differentiated by building typology, location, and is normalized by square meter or square foot. And from this, you could infer how much embodied carbon your building probably will have. And there are, of course, several drawbacks to this, right? So because data is aggregated from different sources, it's hard to control the accuracy of the data. There's also usually a very large spread in these data sets. So as an architect, I feel that they don't really help me that much in designing a building from scratch. Maybe benchmarking in very, very early stages of design. Now, the second strategy, and this is how embodied carbon estimation is typically done, is we have to wait until we get a full building information model, a full BIM model of our building. Then we have the actual material quantities, and we can multiply them by an embodied carbon coefficient. But for this, we have to wait until the very end of the design stage when all the design decisions have already been made, right? And this is, of course, super unfortunate because we don't really want to change our design now that we actually finish the design of our building, even if we get a very high embodied carbon value. And so ideally, we could bring embodied carbon estimation into the very early stages of design, and we need quantification methods that we could apply there and not when it's too late. And so maybe we could use a building massing and then apply embodied carbon values based on material systems that we use for different parts of a building. And so such simplified embodied carbon estimation methods would then use areas of facades, roofs, or floor areas with a multiplier to then calculate the embodied carbon of a structure. Right, so thinking about a building massing, splitting it up into the different floors, and then calculating the embodied carbon based on the construction system that we'd use, maybe a steel system or a system in timber. Now, the problem with these area calculations is that they don't actually tell you that much about the actual material quantities. Every structural engineer will tell you that increasing the span of a structure, for instance, will drastically and exponentially increase the material quantities that are needed to build it. And so it also very much depends on the material we choose. And I want to give you a small example with a hypothetical example of a small spanning system with a primary and secondary span on the y-axis and a secondary span on the x-axis. And on the left-hand side, you see the embodied carbon of a steel structure in a 4x4 meter grid. And you see that comparing it with the same dimensions with a timber structure, the timber obviously wins in terms of embodied carbon. Now, if we scale up the structure and we choose a different span, the opposite is true. Now, all of a sudden, the steel, because it is slimmer in a longer, in a bigger dimension compared with the timber, will all of a sudden be more performative than the timber structure in terms of embodied carbon. And so it's very hard to capture these behaviors into rules of thumb that we can use. And so this led us to the development of new workflows for embodied carbon estimation, where based on volume and number of floors, we create possible internal scenarios through generative structural design, combine them with FEA analysis to then populate and dimension the structural members. And this results in a structural model that reflects somewhat a simplified version of a full BIM model with actual material quantities. And so for a given massing, we can test very many different base sizes, column cadences, or in different directions. And this creates this generative model that then is analyzed with what you would have like a simplified version of what an engineer would actually use to dimension the buildings. And it gives us a very good sense, very fast, in how much material is actually in our building. And so for the scope of the study, we specifically focused on a few steel frame buildings. To verify the workflow, we recreated them using our computational workflow. And the buildings are different typologies. One is a university building, a warehouse, an office building, and a school. And so these real buildings that have been built, where we know the actual dimensions, we then used to calibrate our model. And applying the generative algorithm, we could test material quantities and found that we were actually very close in predicting the actual material and embodied carbon of a building, which makes sense because we use similar pieces of software that engineers use, similar load assumptions, etc. Right? So it would make sense that we would get the same results. And now I want to focus on one specific one to show you a little bit more how that works. So in this case, it was a warehouse structure where in the chart you can see the small dots where each one of them was one simulated version that has a different span plotted with its structural material quantity on the y-axis. So on the x-axis, you have all these different versions of the building with different span. And we can see that actually, if we accurately predict the span of the building, we're in a very close range of the actual embodied carbon of the building. And so we could conclude that actually by knowing the span, which we usually can infer by the typology of the building, plus having a building massing, we can make very good guesses of how much embodied carbon is in a building. And so we can apply this into the design of new buildings. And I'm working on tools that would allow you to estimate that in real time and help architects and engineers to incorporate these things into very early stages of design. And now that we have this whole generative structure, we can also look at the steel elements themselves. And similar to the whole material systems that have very complicated relationships, there are also very important variations of single elements that have non-intuitive carbon implications. So in the case of the different steel cross-sections, they actually have very different embodied carbon value, even though they're all made from the same material, steel. And the chosen cross-section and the length of a member also has huge implications of if they're ever going to be reused, how can they be reused, or what dimension of the steel member could actually be reused. And pushing the generative models even further, we can now use these models to also make element level analysis and figure out what this could mean for the whole material stock of the building, both increasing the accuracy of the embodied carbon predictions, but also allowing us to estimate the material stock that a building has inside from the perspective of reusing the elements after demolition. And so we digitized original building elements, filtered them for different reuse scenarios, and performed a life cycle analysis based on these updated members. And with this, also going from 2D to 3D, we could show that, or we could look at new insight or gain new insights related to structural material quantities. And so in the case of the surveyed buildings here, we could show that increasing the height from an 8-story to a 22-story tower meant an increase of almost 30% in embodied carbon per square meter. Just highlighting how typology is critical when it comes to embodied carbon emissions of a building. We can also start to compare different spans and see that in this case, both buildings show a significant reduction in embodied carbon when redesigned with shorter span. And so here in both buildings, we reduce the span by 25%, and we also see a significant reduction in embodied carbon when we reduce the span. And so in this research, I showed you how we could create accurate material estimates for embodied carbon assessment through generative design, and use parametric models to generate different design options within a predefined building massing. And then linking this geometry creation to automated finite element analysis for structural analysis and dimensioning. And both of these research projects have been published. The first one was setting the ground that I did during my PhD, and the second one was published last year that was focused specifically on the design of steel structures. And so in summary, I could show that geometry level analysis can reveal opportunities for reducing embodied carbon. And these bottom-up models allow for the isolation of specific design parameters, which are crucial in looking at the impact of these specific design changes. And we can use generative design to estimate material quantities, but also tailor structural geometry to reuse. Thank you.